So we were looking at sound propagation in a box or acoustic field in a box, and we derived the expression for the solution for the acoustic field, and now we are looking at the relationship between the wave numbers. So we had the wave numbers kx, ky and kz, and these are not independent things, they are expressed in terms of k0 as kx squared plus ky squared plus kz squared equal to k0 squared. And so if you write the solution in terms of the modes, and then the relation turns out that you can express kz in terms of the ky and kx as follows. It becomes square root of k0 squared minus m pi over b squared minus n pi over h squared per half, and so there is a square root over this quantity which is power half, but this is some quantity minus some other quantity, and if you notice this m pi over b the whole squared and n pi over h the whole squared, they are positive numbers. So there is quite a bit of possibility that the second and third term together can overwhelm k0. So in that case you will get a real solution only when k0 squared is greater than these two quantities. If not, you will get a imaginary solution, and then we will examine what is the consequence of that. So so this would give real roots for kz comma m comma n, and that would mean that you will have this propagating solution of the form e power ik z and e power minus ik z. Now if this quantity becomes imaginary, then you would not get that kind of form because I times I. So if you think of this quantity as imaginary, let us say I alpha, so e power I times I alpha will become e power minus alpha. So you do not get this propagating kind of solution, but you will get attenuated solutions. So you get propagating solution, or in other words any mode will propagate only if this condition is true, that is k0 squared minus m pi over b the whole squared minus n pi over h squared is greater than 0. So if you rewrite this in terms of frequencies, you will get 2 pi f over c squared minus m pi over b squared minus n pi over h squared greater than 0, or we can alternately rewrite this as noting that f lambda equal to c. So you will get 4 over lambda squared minus m over b squared minus n over h squared is greater than 0. This can be recast as this will happen if lambda should be less than 2 over m over b squared plus n over h squared. So your wavelength has to be shorter than certain value for a mode to be established and that mode to propagate. If not, the mode will attenuate rapidly and you cannot establish that mode in the duct. It will only be present locally where you set up the sound source. Sorry. Oh yeah, thank you. So if your lambda is only if lambda is small or the frequency is higher than the cutoff value, you would be able to establish the wave in the duct. If not, this would not get established. It will only be present locally. So if otherwise plane waves should have no problem, because if you have m and n as 0, if you take m and n as 0, this inequality will always be satisfied, so there will be no problem with plane wave. But if you have non-plane waves with this mode numbers m and n, you have to have this condition satisfied. Okay. Now if you think of h is greater than b, I mean if I just pick it that way, the first higher mode will be zero comma 1, that is so you should get lambda less than 2h or f is greater than c by 2h. So if you do not satisfy this relation, you will not be able to set up this higher modes in the duct. Okay. I mean, you can those modes will be very local and the amplitude will decay exponentially. Is this okay? Any questions? Okay. Yeah. Yeah.
So do you think like KZM and it matters a lot if that is plus I something or minus I?
You can choose. I mean, both are possible, but it is. I mean, if you so you have to pick which one is there. So for the left running wave, you will have to pick the solution such that the solution decays to the left. For the right running wave, you have to pick the solution such that the solution decays to the right. So that will be a physical way of choosing it. In any case, I mean, if you have an amplitude at some place you set up, it will decay rather than grow. I mean, that is not physical to have it grow. Any other question? Yes. Yeah, so if you have if you look at this expression, you have to have frequencies higher than certain value. All I done is I replaced f over c with lambda and rewrote this way. So either your frequency has to be beyond some value or wavelength has to be below a certain value. I mean, they have inverse relationship for this relation to be satisfied, and only if this relation is satisfied you will be able to get a real value of kz, which would only be then make it possible to have propagating waves. Otherwise this kz would be imaginary and then you will have attenuated solution. So you will have only a local locally you can establish the higher modes, but it won't stay in the duct for long, for higher distance. Is it clear? Anything else? So I will just pause for a minute for everyone to write these things down.
So when the kz is imaginary, you said decay would happen.
Yeah.
Is the decay for the amplitude or the frequency?
For the amplitude.
Yeah.
I mean that's what the complex wave number means. Complex wave number means the amplitude will decay.
The frequency will remain.
The frequency has a periodic part and non-periodic part. So the wave number illustrates how the amplitude will decay. So e power ikx, if let us say e power I k real plus I times k imaginary times x, so it will be e power I k real times x plus e power minus. So this is the propagating part, so that this multiplied by and this is the growth or decay. So this is the decay part, attenuation part. This is probably a good time to answer the question that you asked yesterday. You asked two questions. One was what happens when you have what is the question exactly about the complex?
Velocity of sound.
Yeah. So if you have a real omega, so okay, let me rephrase the question so that it comes in the video. So when we looked at the attenuation of sound in a duct, we said that there is a loudspeaker and it is producing sound, and we said the experiment is running in kind of steady state. So we have a real omega, and then we had a complex wave number, and the question was whether omega over omega over c is k, omega is real, c has to turn out to be complex for getting k to be complex. So this is indeed right, but what we have to remember is that the way we solved it, it's not a eigenvalue problem. We imposed omega, that means the impedance of the loudspeaker has to match the duct and so on, which we did not take into account. So whatever energy is absorbed by the duct is being given, that assumption is made implicitly. So as opposed to eigenvalue problem where we actually prescribe conditions at the boundary and then we solve for the frequency and the wave number. So the relation between omega and k, that is the dispersion relationship. So in eigenvalue problem you will get a dispersion relationship, and there you can say omega over c equal to k or something like that, and omega can be complex, k will also be complex, but c will have to be a real propagating speed because that is what it is. Now here if you say which I will say, let me recast as k naught into 1 plus I alpha, right. So I will get c equal to omega by k naught into 1 plus I alpha, which can be perhaps written as so. I mean this c is a complex number, but this is just a definition. I mean it is not really the dispersion relationship. We will not get this as the dispersion relationship because there is no dispersion relationship because it is not the eigenvalue problem. So this can be called a complex speed, and people many times call it complex speed of sound, but we have to understand that it is just a definition. So omega over I mean the c, which is square root of gamma RT, that is indeed the speed of the wave which is happening, which comes out as omega or k naught, but the balance is just a way of representing attenuation. But if you are solving a eigenvalue problem, we can actually we will solve in the coming classes when there is a flame and the flame drives or dams, and then you will get a relationship between omega, k and c, and those would be like a dispersion, proper dispersion relationship. Okay, is that clear? And the other question was, when you have mean velocity, would you get same equation? So I worked out the example quickly just 2 minutes before coming here, and I did not get any answer which is fancy. So if you look at so if you let us say we are, so let us say there is a mean flow, but if you travel, we are considering a constant mean flow, so there is no variation in u bar, or there is no non-uniform base flow, it is just a constant base flow. And the question is, can you translate the coordinate system and move with the base flow, and then you should have the regular wave equation. We should be able to translate back and get the equation with the u bar and so on. So what one would do is dou rho prime by dou t plus rho bar dou u prime by dou x equals 0. So this is the continuity equation, and I will replace rho prime equal to p prime over c square. So I will say now so this is the modified continuity equation, and momentum equation was dou u prime by dou t plus 1 over rho bar dou p prime by dou x equals 0. Now if you want to see the so now you are, if there is a mean flow or not, the equation does not distinguish, except that even if there is a mean flow, then you have to be travelling at the speed of the mean flow. That is the way the equation is written. Now if you now get off the frame of reference and sit in the lab and view it from a laboratory frame of reference and imagine there is a mean flow, then all you have to do is to replace this term dou by dou t. We will have to replace with d by dt, which is dou by dou t plus u bar dou by dou x. So I will get two equations which are 1 over c squared dp prime by dt plus rho bar dou u prime by dou x equals 0, and the other equation would be du prime over dt plus 1 over rho bar dou p prime by dou x equal to 0. So now we can do dou by dou x here and d by dt here, and you will get equation which is of the form, let's do it, d by dt, and this is dou by dou x. So need some space. 1 over c squared b squared p prime by dt squared plus rho bar by and the other equation will give so this means that you have to operate d by dt first and then dou by dou x. I don't know how to write it. I hope the symbol is okay, or should I write d and dou? Yeah, I think this is probably more appropriate. And you can actually commute the derivatives, you can check it, and therefore you can get the equation as if you multiply this, so you will get 1 over c squared t squared p prime by dt squared equal to, and now if you evaluate this expression as dou by dou t plus u bar dou by dou x, acting again on the same thing, and check, you should get the wave equation in terms of partial derivatives. And I did not get any fancy things as you are saying. So I will stop here with this. You can check it and get back to me. Right. Just check the full algebra. I am quite keen on clarifying this. Okay. Any other questions on the old topics? Okay. So if there are no Nobel Prize winning questions, we will move on to acoustic fields and cylinders. So having got an idea about acoustic field in a box, and we saw what solutions can propagate and not propagate, now we can go back to our Bessel functions and so on and see what kind of modes can be set up in a circular duct. And usually in engineering applications one finds circular pipes more often. If you go to a lab or any construction, you always find in general in mechanical engineering kind of places you find circular pipes often. Of course in rooms are always like a box. I mean, you don't have circular rooms yet, so I guess both are important. So we look at the solution of we will write the wave equation in cylindrical coordinates, and now we can also do all this in spherical coordinates, but I am not going to spend too much time on this topic. I will just wrap up with this. So we will look at solution to wave equation in general cylindrical coordinates, and this time we will keep all this angular dependence and so on. So we are writing the wave equation, there are no mean quantities separately we are dealing with and so on. So I will take the liberty to drop the primes if that is okay with you. P actually means P prime here, okay. Now we can do, so this is the wave equation in cylindrical coordinates or what is called cylindrical polar. We can do separation of variables. So we can say phi equal to r of r times z of z times. So if you do this and work out the algebra, I will write the final result. So if you work out the algebra, that is you take your pressure as function of r times function of z times function of phi times function of time and substitute it into this relation, and then we divide throughout by r z psi t, then you get something of this form. So this term is dependent on r and phi, and you have this term which is dependent on z, and this is on time. So if you have a function of time being equal to function of z, which is a space coordinate, this should be equal to both of them should be constant, and if these two things are constant, the function which is dependent on r and phi should also be a constant. So that is the logic here. So we can then write this as 1 over c squared d squared t over dt squared equal to minus k squared, and the minus sign is just to make things appear pretty. And you will have the first term 1 over r. So I should have, yeah. So we will have these constant, and they are not independent. We can write a relation between them. So kr squared plus kz squared equal to k squared. So this is like a constraint or compatibility relation. So if you expand this thing out, we can write r square d square r by dr square plus r over So you multiply this through by r squared, and then so r squared comes here, this goes away from the denominator, r squared comes here, then you bring this term on the right hand side to the left side and take this term to the right side. So now you have a function of r being equal to function of phi, and therefore both should be constants. So we will call this constant as minus m squared. So now we have separated out PDEs to ordinary differential equations for each of this r, z, psi and t. Hope this is straightforward enough. So we can write this as two equations actually. So one and the other one is so we have two equations which are actually coupled. So you have the psi, which is the angular dependence, you have a differential equation for that, and you have to note that it is the same m that is appearing here. And what is this equation? You have seen it, huh? Where? Yeah. This is, so here there is this minus, right? No, I want to call it minus m. Huh? Ah. Yeah. No, this is okay. This should be okay. Thank you. Yeah. Again, these are, you can write plus m or minus m, it's just to make the things look nice and so on. So what is this differential equation? What is this differential equation? Bessel equation of order m. Okay, so and we for m equal to 0, that means we if you put m equal to 0, this will become psi is independent of phi. We can get that kind of relation. So we looked at it last class, right, or class before last, and yeah, last class. So this is a more general version where you can have angular dependence, and there are many problems in which there could be angular dependence. So I just leave it there. I will only look at the radial variation, and I will so that so you will get a solution of this form when m is an integer, and if m is a non-integer, what happens? So, right. So this is for m is integer, and when m is non-integer, what is the solution? Yeah, j of m KRR plus j of minus m KRR when m is non-integer. Now the reason we can write a solution in terms of j of m and j of minus m is because j of m and j of minus m are independent independent functions when m is non-integer, but when m is an integer, jm and j minus m are linearly dependent. So then we have to look for an alternate solution, which is what is the Neumann function which we get, and I give you references in last class about these things. If you do not look at them and study them, these will appear as beautiful pictures and not as anything which is meaningful. So I urge you to go and look at those that nice NPTEL video on Bessel functions and so on, or any book or Wikipedia, whatever. Yeah? Without it, I think this will not make any sense. So a general solution is product of this. We know R of R, and we know the solution to this psi would be e power and for z we can get e power I k z plus e power minus I k z, and you can multiply all of them and you can get the general solution. Right. So z is the generalized cylinder function, which can be written as j or y or j of m and j of minus m, or you can also write in terms of Hankel, which is j plus I y and j minus I y. All can be represented by this general cylinder functions, that's z, and the superscript denotes the first kind, second kind. So you always have to have two solutions, right? And m denotes the order. So we multiply this by e power am 5 plus f e power and we have to also remember that this m here is coupled with this m here. So times e power I omega t times, and it's enough to keep e power I omega t or e power minus I omega t, just get the same thing. Thank you. Can I erase this stuff you have written? So next we will study sound propagation in circular tubes. Acoustic fields. And we will look at rigid wall tubes. Now in a tube, if you look at the solution and we have this radial dependency here, and what would be the value of B? Can we guess the value of B? 0. Why? Yeah. So at r equal to 0, the value of y is minus infinity. So he has probably done the homework. No, I think he is an expert in Bessel function. I learned from him earlier. So for those of you who are not experts, you should do the homework and figure out how the y and j likes. So all y's go to minus infinity when r equal to 0. So if your domain includes r equal to 0, you can peacefully drop B will be 0. If your domain does not include r equal to 0, that is if you are talking about annulus and so on, like annular combustion chamber, which you are probably studying, then we have to keep B. Okay, so that is clear. So now we can safely, if you have a circular tube, we can just safely say that our expression is Jm. What is the value of J naught at r equal to 0, and what is J1, J2, J3? 0. J2? Huh? J naught he said is 1, fine. Yeah, all the J's are 0 except, yeah. So for so if you have a circular tube, it is enough to keep this solution, and in summary we can drop this because y of 0 goes to minus infinity, which should imply B equal to 0. So our P prime will go like J of kr, and so we need the velocity. Velocity is 0 if you have a rigid wall, so velocity will go like d by dr. So d by dr of Jm of kr at r equal to capital R, where the tube is boundary is kr. So the roots of this equation will give the values of krr, and in sine and cos you have simple relation, like if sine x is 0, then x can be 0, pi, 2 pi, 3 pi and so on. But we learned that Bessel function has a very important characteristics which about the roots. What does it? Yeah, the roots of the Bessel function are not evenly spaced. So it is a big subject by itself. A lot of people do PhDs on roots of Bessel functions and so on. We will not do a PhD, but we look at first roots of this quantity. So of course there are interesting relationship between Jm and Jm primes. For example, if you have m is 0, J naught prime is, it goes like J1, and then for higher ones there are recurrence relationship in terms of like the primes can be written in terms of other J's, but it is not as simple as sine and cos except in the case of J naught. But handbooks are available, tables are available, and the MATLAB and so on gives the roots very peacefully. So let us look at a table where m is the order here, and 0, 1, 2, 3 we will look at, and we will look at the first root which is nu equal to 0, nu equal to 1, equal to 2, nu equal to 3. So you have a 0 here, but here so this is the very first one that is coming, that is corresponding to m equal to 1, the 0 nu equal to 0. So of course why the roots are this way and a lot of stuff is available, but we can get this from a handbook, and the interesting thing is that this corresponds to the lowest frequency that can be set up with the radial mode, and you can have frequencies that are only higher than that, anything lower than that would not propagate. So you have to have a k which is more than what the kr gives, and what is the value of kr? So sorry, yeah, sorry, fantastic. So k can be written as 2 pi f over c r equal to we will call this root as gamma. So this is the cutoff frequency, the frequency established has to be higher than this for the kz to come real, otherwise you will not be able to get a propagating solution. And so this would, from what we from this 1.84 will correspond to or this will correspond to d, which is 2r equal to 0.584 lambda, which is okay of the order of lambda over 2. So you have to have frequencies which are higher than what you get from this formula to be able to establish radial mode in a duct. Anything lower would only be there locally and you will not propagate, or the wavelengths have to be should be shorter than the d divided by 0.584, or you can think the other way, for a given wavelength the duct diameter has to be like half the wavelength approximately, and anything below you will not be able to set up this radial modes, you will only be able to have plane waves. So the same way we saw in the case of the box, except there it was simple m pi by b and n pi over h, where here we need to have this table or computer program and so on. So I am going to stop my discussion about multidimensional acoustic field with this, but in reality there is a lot more to study. I think annular combustors have these modes which are annular modes, and they are having this radial kind of stuff as well as they are rotating and so on, but we will not speak much about this in this class. We will concern with purely axial waves, but I just wanted to give an introduction to this kind of topic. So I will stop here with my teaching on acoustics, and in next class we will so we have finished the first half of the class, first half of the course, which I said was dealing with propagation of sound. So just to recapture whatever went through half the semester, we derived equations of fluid mechanics, well, one dimensional, and then you can write 3D if you want. But the important thing was that the continuity equation is not rho A V equal to constant, but dou rho by dou t plus del dot rho v equal to 0, and it is really important that we keep the terms d by dt in both continuity, energy and moment. And then we talked about linearizing, and this was purely because we wanted to keep things simple, because linear equations can be solved, and we did manage to solve some of them, not all. For example, everything didn't give out solutions of the form f of x plus ct and so on, only some with the temperature gradient or with the cylindrical coordinates we didn't have a general solution, right. So we linearized, we got travelling wave solutions, we got standing wave solutions, we found the speed of the propagation, which came out to be square root of dou p by dou rho at constant entropy, and then we talked about different kind of boundary conditions, closed and open ends, and then impedance boundary conditions, and then we talked about how to determine impedance in a practical experiment. We said that it is easy to see the solution and then get the boundary condition, that is what you do in reality. And then there we set up a real frequency and looked at the standing wave structure, got the impedance, but then we were able to translate it to the eigenvalue problem with that end, and you are able to get the real and imaginary part of the frequency. Real part is periodic solution, correspond to periodic solution, the imaginary part corresponds to exponential growth or decay. So we linked admittance to the energy flow, and that we linked to the growth or decay, because if energy is coming in from the boundaries, your acoustic energy in the duct will grow. If the energy is going out, your energy will decay. And then we looked at sound propagation through non-uniform temperature, regions of non-uniform temperature, then attenuated waves and so on. And then lastly we looked at we also looked at combination, when there is temperature gradient and when there is damping, and then we looked very quickly at multidimensional acoustic field, that is you have like a acoustic field in a box and acoustic field in a tube. So of course this is a big subject, and the 3 semester classes on acoustics, but I have crashed everything into 2 months or something like that. The idea is that the second half of the class, which will start from tomorrow, we will speak about thermoacoustic instability or the combustion instability, and this is more like a background towards that. So we, in summary, we studied propagation of sound, and we are going to look at generation of sound. Okay, and why it should have been the other way, but propagation is much easier to study compared to the generation. At least propagation is a well established subject. Thank you.